Hello, everyone. Hope that you are enjoying the summer school. So I'm happy to introduce here Lucas Dixon. Lucas is a principal research scientist at Google DeepMind and a colleague of PAIR, a People and AI Research group working on explainable AI. Previously, he was chief scientist at Jigsaw within Google, and he has been working at Google with different areas and with different roles, closer to more application and more research works. And after doing a PhD at University of Edinburgh on automation of mathematical reasoning and working also as a research scientist there. So thank you very much.
Thank you for the introduction. It's a pleasure to be able to talk to you today about building with sequence models. So this morning, you had some great lectures on sequence models. This should mostly whet your appetite for understanding transformers tomorrow as well. But I'm going to talk a little bit about responsibility and prototyping. And so to give some context, there's a particular point of view that my research group, People in AI Research, takes towards this. So the mission is there, but I think the point of view is the most interesting thing. And it's inspired by the concept of boundary objects, which I'm told originated in a Scandinavian design movement, but are popular in sociology as well. And these are objects that connect different stakeholders to understand the same fundamental phenomena. And my favorite example of this is architectural diagrams. Architectural diagrams connect the person who's going to live in a building to the person who's designing it, to the people who are building it. And so the question we then ask ourselves is, what are boundary objects for artificial intelligence? And some of my favorite ones are open source software tools and also platforms. These become artifacts that connect you to AI, and they connect many different stakeholders. And I'm going to go through a few examples of the ones that we've worked on so far, and then I'm going to dig deeper into where this comes about. And of course, research papers themselves are artifacts that connect different stakeholders, but that's primarily like the research community. The interesting thing about software artifacts is that they can connect very different kinds of stakeholders together. And so here are a few different ones that we built. AI Studio is probably the one that's best known at this point in time. It's the main way that people work with Gemini models. But we also have a guidebook to explain, particularly for designers and product managers, how to develop with AI. And then there's lots of more specific tools, like there was a tool called Know Your Data to understand the data sets you're working with, which are normally less often looked at than maybe they should be. LLM Comparator is a tool to try and connect different stakeholders to the evaluation of models, if you're trying to understand if one model is better than another. We've got tools for understanding training data attribution, which I'll talk more about later, and also tools to try and understand how is it that groups of people together interact with AI. So if you have an AI inside a chat group, for example, how do you study that phenomena? So first of all, I'm going to tell you a bit about how I think about large language models. And this is going to be the high-level framing, and then I'm going to dig into why. So actually, the first rule of thinking about language models is don't think about language models. That was a small giggle. I guess most people haven't seen Fight Club. Oh, there we go, a bit more. The reason I say this is that actually what's interesting about language models is not the language model per se. It's actually that language models let you drive computation. The human language becomes the interface to interact with computation. And that's something that's very different. So in a way, the real power here is for building with AI is the ability to control computation with language. That means calling APIs, making images, music, controlling robots, so on. So the way I think about language models is somewhere between an interpreter, an improv comedian, and a fuzzy database of the web. So improv comedian, because generally they will start with whatever you start with, they will continue with it. An interpreter, obviously, because they can explain different things, translate between languages, and a fuzzy database of the web because they tend to recall some fragment of things that have been seen on the web, which is one of the primary corpuses for training them. LLMs are by far the most configurable artificial intelligence that we've ever made. This is why you end up with papers like this, which are going, wow, the generality of the configurability allows them to solve many different tasks. So, but I think probably the right metaphor here is something like Play-Doh. You can make many different things with Play-Doh. And in particular, one of the great things about Play-Doh and LLMs is that you can prototype far faster than you ever could before. So this poses two interesting dynamics. One of them is that you can release an application much quicker than you ever could before. You can spend a week building something and launch it, basically. But also, it means that you can get feedback on its usage far faster than you ever could before. And I'll give you some arguments about why that actually, in many ways, is a golden era for responsible AI development. If you can actually understand what the real issues might be when someone interacts with your software, with your product, you're going to end up knowing far more than you did before. And this is because actually, very often we fail to anticipate the problems of software until we actually start observing people using it. It completely changes the way you think when you start getting a prototype and observe people interact with it. The other, I think, key concept for me is the jagged frontier. There's obviously many amazing things, and people spend a lot of time telling you about the amazing things language models do, and I will do some of that as well. But there's also many amazing failures despite their amazing capabilities. And it's somewhat a game of cat and mouse, because every time a particular failure becomes well known, people tune the model or do something else to try and make that particular class of failures go away. But one of the most recent branches of these kind of failure of language models to really generalize in some way you might expect, of course, is the illusion of thinking paper by Apple, which also has many critiques leveled against it. But it's a very interesting that there's a very significant branch of research on the limitations of language models, and at the same time that we see these amazing things they can do, whether it's like the ability to write code. Yesterday, OpenAI and Google both announced that their language models had competed in the Math Olympiad and both had won gold. Although if I want to make a little bit of an elbow jab, the Gemini models actually were rated by the AMO organizers, where OpenAI rated their own models. But probably they're both just as good, really. Okay, so overall, I think the way I think about it is that language models are much more like a material than they are a medium. Chatbots, I think, are a medium. But language models themselves are a material. You can build far more than just chatbots. So I was very, very happy at the end of Noah's talk of his encouragement to think beyond chatbots. I 100% agree with that. And we'll look at a few things at different levels of scale there as well. So first of all, language models. You probably don't need very much of this, but language models generally are initially trained as autoregressive machines that predict the next most likely word. And they do it with vectors. We have a sampling strategy that rolls some dice to predict what actual token to pick. It picks one of the token, add it to the input of the model, and repeats. So but even in this very simple description, there's some amazing weirdnesses. So it's a bit less of an issue now, but it was very apparent a while ago, and it's very apparent when you quantize models as well. But if you set the temperature too low, language models very often end up repeating themselves. They get stuck in these strange loops. It's not very well understood why that happens. And of course, if you set the temperature too high, you also end up in much more random output, which just doesn't make sense. So there's lots of things where we have a kind of engineering discipline or a sense of what to do, but we don't necessarily have very good theory for it. And so there's an example of one paper here looking at the role of quantization in this weird repetition behavior. But this is to say that there's lots of interesting things, even in the very basics of language models. Okay, so this is going to be a significant part of the talk, controlling language models. So if language models are a medium, a material, how is it we build with it? What are its properties? So first of all, I'm going to give a landscape. So this landscape is I'm dividing somewhat arbitrarily, but I think it's a useful decomposition nonetheless, the control of language models into 4 stages. There's pre-training. Pre-training is very slow, very expensive. And it's also very often incompatible with downstream goals. So this was highlighted in a very interesting way where people have taken and tried to detoxify the training data set for language models. And you can do this. You can run a toxicity classifier which has relatively high ROC AUC score and remove lots of toxic things from your pre-training. And you train your language model. And the result is a language model that cannot distinguish between things that are toxic and things that are not. It can't understand what is hate speech and what is not. So not only is modification at pre-training extremely expensive to iterate on, it can also have undesired downstream consequences in terms of the basic capabilities. Post-training is typically where you tune all the parameters in the model as well, but you train it typically at the first stage of language model development for following instructions. So we want the language model not just to continue what you say, but we actually want it to follow instructions. That was it was very interesting because the moment when ChatGPT really kind of blossomed was because they had tuned it to follow instructions. And it's actually a very small delta between a pre-trained model and an instruction following model. So, and well, I'll talk more about that later. Then generally after you've got your instruction tuned model, which does what you want, people then typically want to configure it for a particular application. So that's the last two buckets. So for parameter efficient tuning, this is when you say, actually, I'm not going to change all the parameters in my model. I'm still going to use, stochastic gradient descent and update some parameters, but I'll update just a small number of them. It's relatively sample efficient, meaning you can typically train it with between 100 and 300 parameters, examples, I mean. It's also relatively fast to iterate on. And one of the fun things is you can actually serve all your variants of your model in one serving stack, because you can provide the small number of parameters at query time, like you do with input text. So it has this very interesting in-between. And then, of course, there's prompting, which you probably all know, which is very sample efficient. Right? You can just give an instruction. Maybe you don't give any examples. This makes it incredibly fast to iterate on. You just change your instruction, try again. However, when you work with plain text modifications, it's much less clear how you make it better. The notion of how you improve quality when you're modifying the prompt is much less clear. Whereas in parameter efficient tuning and post-training and pre-training, we know that you just, you add more data and it'll generally be better. There's another thing here that's important, which is that this is a conventional wisdom. And the conventional wisdom is that the core capabilities of a language model are developed in pre-training. And then in post-training, they learn how to follow instructions to use those capabilities. And sometimes things go wrong. There's been many, many papers describing like the way that you end up narrowing the actual capabilities as you do post-training. And so there's a real tension here that if you put too much data in post-training, especially if there's like unintended uniformity to the data, like, oh, every time you reject someone, you say, I'm sorry, then that means that actually your model ends up being less able to distinguish the cases when it should say, sorry, I'm not able to do that versus not. So there's a kind of like a potential collapse that happens there. And then finally, in parameter efficient tuning and prompting, it's typically when you actually make the LLM do what you want. So we'll go into that more as well. But let's look a little bit at prompt templates. So prompt templates are the main way that most startups and most people doing control of models do it right now. And what they do is they create a piece of text with a hole in it, and they substitute in just at query time what's going to be inside that text. So this on the right-hand side here is my movie recommender. I've slightly minimalized it. So, I've seen The Fifth Element, and I thought that was, this joyous sci-fi. And I've also seen Seven Samurai, which, I think is a great, I love the cinematography in it. I think it's atmospheric, it's great. And so then what I can do is I can put in a new movie into that input text, and then I can just let even a pre-trained language model here, let the pre-trained language model, or it'll actually be the same with post-trained largely, and it will then give me a summary for a movie I've not seen based on the distribution I've just put in. So for me, this was one of the amazing things. And there's tons of tricks with prompting. Chain of thought reasoning is one of the most well-known. But the notion here that you can make a small application in a little piece of text like this, a few years ago, people working on recommender systems, the configuration of the recommender system, your taste, was a completely opaque object. You would never have access to it. You wouldn't be able to modify it. But that doesn't have to be the case. So there's a lot of interesting scope here just with prompt templates. So also a bit of jargon, since this is a summer school. We've got zero-shot templates where you just give, and in this case, it's with an instruction. I want to give you the taxonomy of templates here. So we also have few-shot. That's the middle one. Also in the example, sometimes people provide structured text as the input and output. So this is a few-shot prompt with no instruction. And it only has one input. And on the right-hand side, here's a chain of thought thing where it's intended to give a description. It's given some preferences, given some input, and then it gives you a description before telling you what your recommendation should be. So in this case, you have, I think the general taxonomy is instructions, whether you include few-shot examples, explanations and thoughts, and structured syntax. That's the kind of main four-part taxonomy of how people build with prompts. And so let me give a concrete example of why I think this is amazing. So this is now, we've gone away from the jagged frontier, and we're just saying this is amazing. So in 2016, 2017, I worked in a team in Google, and we were working on trying to understand the emotional impact of language. And that was kind of hard. So we said, okay, let's instead model what makes people leave a discussion. At what point on the internet are you just going to slam your laptop, throw it out the window, give up on the conversation? And so, in order to model that, we collected 2 million comments. We had every comment rated by 10 people, not the same 10 people. There was thousands of people. And we spent a year developing this. We worked with ML experts. We had a team of about 15 people, and we built a thing called Perspective API. It was at one point it was serving traffic about a quarter of the scale of Google. It was very widely used. A third of commenting platforms online were using it. Facebook made an implementation of it. Twitter did the same thing. It was a classifier got like 98 ROC AUC score, and it was as good as 3 annotators. Now, crowd workers are not maybe the best bar to set for your training, but it was widely used and widely useful. In 2023, with parameter efficient tuning, 80 examples, which were created in one day by one person who didn't know about machine learning, they were able to create a classifier with about the same quality as you would have got from using existing, huge investments in 2016, 2017. So that's a scale of thousands of times cheaper and more efficient to create text classifiers. And on the right-hand side here, here's a small text classifier. And actually, I should say at the same time, this method won an ACL semi-val competition trying to identify and explain sexist language. So it's a very, very big change in what was possible. And this example, I think, highlights it's not always just chatbots that change. Actually, fundamental basis of classification has completely changed in natural language as well. So modern prompting looks a little bit more complicated. Modern prompting actually consists of system instructions. Those are ones by the model provider, typically. So, some people publish them, like Anthropic, which I like. Some people don't publish them, which I like less. Developer instructions. So those are typically a section by, if you are a developer, you put your instructions about what you want. And then finally, the user expresses what they want. Then you have some control decoding parameters that controls the temperature. Maybe it contains some additional constraints, like only output yes or no for the like. And then for the string, any valid JSON string would be great, right? And then you combine these different things together into your input for your system, into basically a big text input. And then your system maybe makes calls. Maybe it makes calls to Google search. Maybe it runs some code. It's got a set of things that you've given it. And then finally, you get your output. So this is essentially the way pretty much all modern LLM-based startups are building applications right now. But there is another thing that people often do, which is retrieval augmented generation. So I just gave you the modern prompting on the left-hand side. It's basically query, template, LLM. But very often you have a very important problem, which is how do you get the right information into the context of the language model? This is important because language models work far better with the right information in context and without too much information in context. If very modern language models have like 1 million tokens of context window, at least the good ones that we make it do. That means you can fill it up with a lot of stuff. But if you do that, it also makes the language model very slow. And it gets confused from what's in the context. And there's lots of papers describing how different aspects of context addition can confuse it. So retrieval augmented generation was like, okay, what we're going to do is we're going to index a whole set of documents that we might want to include. We'll index them via some small embedding, and then we'll retrieve that embedding depending on what the query says. And so there's lots and lots of different embedding models. And then what you do is you plug the different things that came back from the database into your template. And that's great for working with very large amounts of data, but it's not the only game in town. So also we have context engineering, right? Context engineering is like, well, what about if I just write some custom code to figure out what gives in the context? And context engineering and agentic systems are almost the same thing if you squint at them. So typically, context engineering involves either retrieval augmented generation or even very simple things that many code editors do, which is, make a list of the files, make a short summary of each file, and then just plug that into the language model and make a second call. Say, okay, which files do I need to load? These are the files I need to load, plug them into the context, and then run your execution. So now you basically, you can pay with additional queries. Now, paying with additional queries is a very common pattern. The more queries you pay with, generally the more you can boost quality, but you have to obviously pay for it. So agentic systems and prompt chaining, I think this is one of the earliest papers on prompt chaining. It's a very active area of research. There are tons of frameworks. And I guess one of the things I would say is that no one actually really knows what the right way to do this is. I think if you're thinking about like directions to go in. I think that there are tons of people here, so it's a very crowded space, but also it's relatively early in the experience of software development of how is it that we develop AI-based, generative AI-based systems that do what we want. So, but there's one amazing thing that you can do that is a very general pattern, and I'm going to call out, which is you can usually spend inference for quality in a very specific way. It involves knowing what you want. So, knowing what you want is a very powerful paradigm. If you know what you want, it's much easier to get it. It's hard to get what you don't know. There's a very naive strategy, right? Which is, if you take a 1 in 100 success rate model that outputs the right thing 1 in 100 times, but you have something that can check if it's the right thing, but just can't generate it, then by simply sampling a lot more, you can boost up your quality. This is very profound. It's very expensive to do. And so then what people have been doing is in developing smarter ways to essentially do sampling. And some of the most interesting ones right now are if you have an actual program that can give a score, then what you can do is iterate. So you generate an initial response from your language model, and then you say, well, how do you make this better? And you can ask the language model. So this is essentially genetic programming with a custom mutation operator. And then often you don't actually have a good notion of what you want. So instead what you do is you create a prompt for a language model and ask the language model what's good. And so then, of course, you end up with like a set of comparative ratings is the most common one. And then you end up applying measurements like ELO scores. So these two are two approaches that have both got a little bit of press. The one on the left is called co-scientist. And its goal was to accelerate scientific breakthroughs. There's a couple of experiments being explored by UCL and by Stanford at the moment, inspired by suggestions that it has made. And on the one on the right is one of my favorite ones, which is AlphaEvolve, which is exactly this notion of let's make a sampling method, let's evolve the suggested programs, we'll have an evaluation and we'll have a pool of programs that exists and we'll sample from them and we'll just iterate the process. And this is actually kind of amazing. Like the fact that you can make a language model just iterate on its own, and the result is, so I put a couple of the results here. It has made 4x4 matrix multiplication better. It saved 1% on Gemini training time. It's 32% speed up on flash attention. So these are all, and also it solved the capset problem. So it's done foundational computer science advances, and it's made incredible optimization speed ups. And it basically, if you look at it, it will end up like eking out all the corners or clever combinations of things that no one would ever bother to spend that much time doing. It's actually a very interesting thing, a very interesting way to spend compute and get quality. Okay, so we've talked about how you control AI. Let's talk about what responsibility means and the role of prototypes. So responsible AI means many things to many people. Generally, it's something to do with ethical principle and societal values being built into the development of your AI. And so one of the breakdowns is don't do bad things and make sure you do good things. And I think responsibility has those two edges, right? The Socratic oath is one, right? You say, okay, if someone needs help, you're going to help them, right? The doctors take this oath and say, well, if someone is sick, I promise I will help. And actually, I went to a PhD defense in France recently, and they have a similar thing. When you get your PhD defense in France, you make an oath to science and advancing science. So it's a very beautiful thing. So going back to responsible AI, some of the things we don't want to happen. So there's a big class of errors around fairness. I'm going to go into a specific example of that shortly. But there's some important things to know about fairness. One of them is that the definitions are inherently incompatible. There are lots of definitions of fairness, but you cannot have all of them. So you have to pick what you want. The example I gave earlier with language model pre-training is a phenomena that actually is even more generally important, which is what do you actually want your language model to do? Do you want it to reflect the reality of text on the internet? If you do, that allows you to do things like simulation. If you can do simulation of people dynamics, maybe you can dramatically improve mediation or the way people work together, right? On the other hand, if you try to mitigate that behavior, you can maybe make the language model somewhat fairer. So it's a very challenging problem. Are you trying to reflect reality or some creators' ideals? Another big branch of things we want to make sure are good is, transparency and explainability. You don't want your system to be incomprehensible. There are now laws around this as well with the EU AI Act. And so in this space, actually, I think interpretability methods, which I'll go into a little bit more depth as well, have actually made some pretty impressive progress, and there are still many challenges, but lots of good work to do. Privacy and security, well, of course, one of the main complications is that language models can memorize what they're trained on. And if they memorize what they're trained on, then maybe will end up giving away personal information that you don't want. Safety and alignment is generally the idea that, like, actually, we're trying to align it to human values, but what are those values? Are those the values of the system, of who's developing the language model? Are they the values of the developer trying to create a specific application? Maybe it's trying to create a companionship bot or something like that. That might be a very different set of values. And the end user might have very different values again. There's significant concern right now around misinformation as well. And of course, there's the environmental cost of running and training language models. So those are all the things to watch out for on that side. On the positive side, though, we may have a responsibility to use language models to do good things. Some of the ones that I think are most exciting to me is the advancement of science itself. AlphaFold has helped figure out new drug discovery. AlphaEvolve made advances in foundational computer science, and AlphaProof is also helping try to work with advanced mathematics. So lots of things in science and mathematics can be advanced. There are customized models like MedGemma that work specifically to try and enable medical applications. In the case of MedGemma, it's to do medical diagnostic. We might hope that language models would democratize software. Perhaps it will automate bureaucracy. I don't know how many of you like doing taxes. I think education is another aspect that people feel an important role. Like, on the one hand, I think language models actually introduce a lot of challenges. At lunch today, we were discussing that the fundamental motivation to work hard is more difficult when you have a very easy off-the-shelf thing to help you. If you have a language model and it says, oh, okay, I can tell you the answer, it's much harder to invest the energy in working through it yourself, especially on pen and paper or something like that. And at the same time, that struggle is necessary. But language models can also assist you in learning a lot more things a lot quicker. Anyone who's done coding knows that when you work with a library or an API that you're not used to, language models are incredibly helpful, far more useful than browsing Stack Overflow or God forbid, actually reading the documentation. So, and then of course, the last category, which is one I feel particularly strongly about, is misinformation polarization. While generative AI is also being used to propagate or generate deep fakes and other problematic content, people are also using it both to catch the content, but on the social side also to understand the dynamics with people. One of my favorite bits of work here by David Rand, by David Rand's group a couple of years ago, is using chatbots to have conversations with people who have conspiracy theories. This was generally in psychology thought to be a dead end. There was generally thought that you couldn't do much here. But actually, it turned out that some element of the sycophancy of chatbots was useful. They're like, yeah, that's a great thought, but have you read this or have you thought about that? It turned out that the kind of infinitely kind chatbot was much, much better than I am at engaging people with radically different views. So it may be actually there's some hope for language models to play a mediation role. So this is a broad overview, but now I want to tell you a short story. I'm going to go back to Perspective API. So, I told you this, and in case you were curious, this morning there was these very nice talk about, CNNs and LSTMs and RNNs. So Perspective API was, first of all, a CNN. This was kind of unusual, but it actually turned out to be a very practical and efficient way to develop language model classifiers at the time. These days, it's transformers, of course. But, we released it. It was kind of exciting. It was measuring if people would leave a conversation. But then we got some very interesting feedback on Twitter. We had actually one small anecdote about this that's fun. On the internet, if you try to find horrible comments, what fraction of comments on the internet are actually would someone judge as rude, disrespectful, or otherwise likely to make you leave the discussion? Any guesses? 3%. 3% is actually a relatively reasonable percent. It's actually between 1% and 0.1%. So most people's perception is like this. It's and he was actually like 3% is actually low. Many people's perception was much higher. Anyway, so the thing is, if you're training language models and you have a 1% or 0.1% toxic comment ratio, the language model can get a very high accuracy by just saying everything is fine. And saying everything is fine is not very helpful. So you have to work incredibly hard to find toxic comments online, actually. And so, we had a whole bunch of bootstrapping ideas and things we did with that. We largely got comments from news organizations who donated them in exchange for API access, like New York Times did. The funny thing is that the most toxic place on the internet that I have found was actually the input box for the Perspective API. We had a public demo. People would write really horrible things in there at a much higher ratio than anywhere else I could find on the internet. Anyway, going back to the story, we found, people, when we put this text box up there, people started reporting screenshots like this. Black trans women eat can of pears, really enjoys it. And, it says 61% similar to comments people said were toxic. Like, well, that doesn't seem right. That doesn't seem like it's got anything particularly toxic in it. However, if you look at the raw distributions, this is some examples. These were 3 comments that give you the scores of the initial version of the model. And you can see here that if you look at the overall distribution, that's the top left here of the original toxicity data set. The overall distribution looks like, about 30% toxic comments, which we were very proud of. But if you look at like the subset sampled containing the word gay or transgender, the distribution is almost entirely red. What happened, of course, is that CNN was like, oh, wait, this is a trigger word. Yeah, so it was like, oh, that's really clear signal. So fundamentally in the data set, we had an over distribution. And there was 2 reasons why this was interesting. One of them is that we spent quite a lot of time consulting with different academics who were like trying to think about where would bias be in language models. And people were like, well, oh, bias will be in the annotators. And it's not that there's no bias in annotators, but just in your raw data distribution, there's an enormous bias, and it completely dwarfs the bias in annotators. So if you take comments, your fundamental sampling strategy generally has biases that you do not intend. And of course, the fix here was actually quite simple. The fix was, oh, well, what we need to do is we need to sample from comments containing these words that allow the model to distinguish between when it is a toxic use of the word and when it is not. And so we do that, we rerun training. It took a couple of weeks. And it was like made a huge difference. It was like, oh, okay, there's a very big difference. But the really funny thing is actually, what was the effect of this? Actually, I'll go back. Any guesses? I slightly spoiled it, but you can still guess. I don't mind. So the effect that people feared was that comments by groups who use these words would be diminished on the internet. You'd actually compound groups of people who are using this word positively, who already had a hard time talking on the internet and not getting abuse for it. The interesting thing is, that isn't quite what happened. So this is the actual application that we had at the time. So we were working with the New York Times. New York Times had a pre-review process. So they review all the comments, and they review them sorted by toxicity. So they look at the most toxic comment first, and if the comment was toxic, they would not publish it. If the comment was fine, and they had a very high standard actually. They don't. It's a privilege to have your comment published in New York Times. It's not a right, unlike other websites. They tried to hold it up to high journalistic standards. Anyway, so if your comment was good and contained, one of these words, it would be top of the list. And so the very first comment to be published, the one that has highest visibility, the one that is most seen and most discussed, would be the comments containing words like gay, transgender. So it was actually the exact opposite of what everyone feared. The actual impact on society was the opposite of what everyone thought the model bias meant. And that was a really eye-opening moment, because what that means is actually the impact on society is dependent not just on model, but on the UX, how people interact with the model. What is the prototype you build? And this is one of the main reasons I think that prototyping actually represents a kind of golden age for responsible AI. You can build a prototype, you can look at what happens with it, you can see what the dynamics are much, much quicker than you ever could before. Like Perspective API was a development of a year at the time and a significant investment. Today, we'd build the same thing in 10 minutes, and then we would start looking at what the dynamics are. And of course, the other thing I should say is that if that sort order is reversed, instead of promoting comments with these containing these words, it would actually diminish their visibility. So the visibility effect on comments containing words like gay and transgender is dramatically changed simply by a sort ordering in the in the interactive thing. So we were then faced with a difficult problem. What should we do? Should we leave the model as is? It seems to be correcting some sort of background societal bias. Maybe it will end up equalizing in the world. Or should we try and not change it? Any recommendations? We had to fix it because this wasn't the only application we wanted to be used, right? We had many applications in mind. So we're like, okay, that wasn't the actual intended bias of the model, even though it was one maybe we were, temporarily kind of like, oh, that's kind of cool. But so we changed it. We made these fixes. And today, if you take that 5-minute toxicity classifier that I showed you a few slides ago, it actually has very few of the unintended biases because language models today are much, much better at context. They are far better at being able to model the context of a comment and understand the context in which a word is used. So you still have biases, but you have to choose them now. The biases in a language model are dependent on the prompt text. And you have to think about, well, what is the bias that you want? Every language model is a bias. Otherwise, you would end up with gibberish text output. So it's a bias towards a distribution. Which distribution do you want? The prompt text itself controls that distribution. Okay, now a little pause there. I'm going to do just a couple of questions, and then we're going to dive into some interpretability and then wrap up. Anyone want to? We've got one question there.
On your temperature sampling slide, could you explain what you meant by if it is greedy decoding, you have more repetition?
Yes. One of what happens is that the output of the language model will very often end up into some kind of infinite loop. So it will generate a repeated subsequence of tokens continuously. And this is a particularly, you'll still see this if you take any open weight model, you heavily quantize it, and then you write something in. Very often you'll find, and you greedy sample, very often you'll find that the language model ends up in this strange infinite looping behavior.
I see. Thank you.
Hello, thank you for the talk so far. I have one question related to the post-training. I have one experience on reasoning on a small data set, MGSM, and I noticed that during reasoning, these models tend to not follow the way we would want to reason. For example, if we say that reason in a sequential way, then it sometimes says step 1, I'm going to do this, step 2, and sometimes it just doesn't follow. It starts with the curly braces. Sometimes it starts with the bullets. As this data set was really few, so we were able to go over them very quick and make a rule-based and trim those and made them really like the way we would want it to be. How would company like Google would use this when they would post-train on a large data set on large data?
Thank you. Sorry. Was the mic off before when I responded to the previous question? I'm sorry. Yeah, there's two aspects to this. One of them is that you put lots of data into your post training where it follows the instruction. That's fundamentally a failure to follow the instruction. The second way you do it is I've put it here, decoding controls. Many language models now include some mechanisms for semi-structured output. So you can force it to say, oh, I'm going to start with a markdown heading, put in some text, then I'm going to have a new line, and then I'm going to have a markdown bullet, and then continue. And by providing a constraint to the decoder, which is essentially a finite state machine, it's essentially a regular expression, right? Then you can end up getting very, very strong forcing on that prior, making it sure that it falls into the right place.
Thank you very much.
I slightly worry that the previous question, I had the microphone turned off. Okay. If anyone has a burning desire to hear it again, please, you can ask me at the end or ask me now. Okay, so we did some stuff on responsible AI and prototyping. I want to talk about understanding the material. So large language models are like a material. We build with it. I've given you some ideas of how you control, basically how you build with large language models. But what about understanding its nature? There's an interaction between understanding what language models are and how they do and what you can build with them. So this is the kind of high-level picture, right? We have prompt that comes in, we have a model, the parameters of the model are conditioned via training examples, and that produces model behavior. And then, like I just demonstrated, model behavior may have unintended distributions, and there's a system that uses it, and that might result in potential harms in the world, or it might actually end up helping them inadvertently if you get lucky like we did. So in terms of understanding control, then, there's a bunch of dynamics in here that we can look at. So what I'm going to look at, first of all, is probes. So probes work on the activations. So within the language model parameters, you have certain vectors that are generated dynamically through the execution of the language model, and you're going to learn all about transformers and this tomorrow. But probes basically train a small logistic regression model off the internals of a large language model. When probes are applied to a large language model, you can apply probes in many settings. But I wanted to highlight this particular example because there's a very nice bit of work by Martin Wattenberg and Fernanda Vegas, which is this one on the right-hand side, where what they did is they made a bunch of probes in the model to measure whether the model believes that the user is male or female. And what age do they think the user is, and what socioeconomic bias is, or socioeconomic status do they think the user is. And then once you have a probe, you can invert it for control. So you can play games with counterfactuals. You can say, well, what if you thought, actually, I was a man or a woman? So one of the interesting things they found, and this was done on llama models, is that men and women didn't get the same length of answers. Men got, what do you think, longer or shorter? Put your hand up if you think longer. Men got longer, we got some hands. Put your hands up if you think women got longer answers. Right. But it turned out to be the opposite. Do you know why? It turned out to be opposite because the models were giving very vague, general, uninformative responses to people who it thought were women, and it was giving much more detailed ones to people it thought were men, which isn't really what you'd want to happen. So by creating probes, you can understand the dynamics of the internals, potential misbehaviors, and you can explore it. There's lots of other fun things. Definitely recommend this paper if you're interested in this kind of area. So probes let you basically look at a little fragment of the internal of a model. Now, probes are also easy to get wrong. It's very easy for probes to have an inadvertent, to capture inadvertent things you didn't want them to capture. But generally, they're one of the most robust ways that we have for language models. Saliency methods are another one. So saliency methods, instead of looking at the activations, they typically look at the gradients. So that's like, how would you change the model? So this is a little example I like because it's actually a prompt debugger, and I haven't seen very much of this usage. In fact, much less than I think it ought to be. So this here is a prompt that is meant to be a food recommender for a country where you don't know what food is, and maybe you have some dietary requirements. So I don't understand Portuguese, so maybe I would like to know what I'm eating, especially if I can't eat something. Maybe there's some kind of fish I can't eat or something like that. So in this case, the few shot prompt here is a few examples of things people like and don't like, and at the bottom we have like, okay, this is an example set in France in case you want to come and visit me in Paris. It says, taste likes, I like cheese. Taste dislikes, I can't eat eggs. Suggestion, quiche Lorraine. It says, analysis, it's a savory tart with cheese and eggs. Recommendation, you might not like it, but it's worth trying. It's probably not worth trying if you cannot eat eggs. And we're like, well, why did this happen? So it turns out what you do is you measure the gradients over the tokens of the model from the output. And when you do that, you can find out which few shot example was the one that was most informing the reasoning. And so in this case, it was exactly the top one. And so here you can see there's a typo. The top one is like, I have a sweet tooth. I don't like onions or garlic. Suggestion, onion soup. It has onions in it, which you don't like. And then the recommendation is you have to try it, which was copy and pasted perhaps from the third example. Has anyone ever made a typo in a prompt? Yeah, I imagine so. So where would you find your typos? This is an idea that by looking at the output example, you can find and correct your typo. Patch scopes is one of the most interesting ways for me in terms of interpretability. So here the idea is that you can take the internals of a language model, the activations, and you can paste them over somewhere else. So in this particular case, we've got Amazon's former CEO attended the Oscars. And this diagram is a view of the activations in a transformer model and the information flow. So if you take, Amazon's former CEO doesn't mention the word Jeff Bezos anywhere. Now, if we take the very bottom here, if you take the bottom gray box for CEO, that's the embedding for CEO. If you paste that into the right-hand side, that's a few-shot prompt, and the few-shot prompt basically repeats whatever token you put in. So if you put in CEO, the bottom representation there, it will output CEO. If you put in the top one, which is likely to be attended, because that's the next token it generated, if you put the attended token there, it will generate attended. But what's interesting is that in the middle of the model, there's a sweet spot where it suddenly starts to generate Jeff Bezos. The model, according to its own interpretation of the internals of its representations, is able to view, oh, there's the information of Jeff Bezos there. And this gets really fun, right? Because now you can say, well, okay, let's take the source prompt, Alexander the Great, and we'll paste it into this few-shot prompt, which is, a word and then a short description. So Syria, country is in the Middle East, Leonardo DiCaprio is an American actor, Samsung is a South Korean multinational, blah, blah, blah. So now we take the word great, the token great, and we do patch scopes on it. We paste in the internal representation of great at different layers in the model. And at the very bottom of the model, it's like, oh, this must be Great Britain, because Britain is obviously the most common continuation of great. Maybe, I guess it is in a language model. But if you go up a layer, it jumps to Wall Street crash, which is probably a reference to the Great Depression. Then, the Wall Street bubble, Great Depression, clearly a reference to the Great Depression. Wall Street, it goes up a level again. So still something about Wall Street here. And then, but by layer 5, suddenly it switches to being ancient Greek ruler, which is, that's actually what the reference to Alexander the Great. So at this point, we can see that the internals of the model have encapsulated a range of reasoning, a range of the inputs. There are lots of other fun things. We're running a little bit short on time, and I'd like to leave some time for questions. Training data attribution, I'll just mention it briefly, because I think it's another fascinating area of interpretability. It's basically what training data is responsible for the model's behavior. And so this is an example where we developed a classifier, introduced some noise, and training data attribution is basically you treat the model, or one branch of it, is you treat the model as the model gradients as a giant vector. And you go, well, what other things produce a similar vector? And so in this case, we're able to then significantly recover classifier behavior. And so this is a kind of picture. Counterfactuals is just changing some aspect of the input here in the prompt. Probing and patching work on activations. Saliency and TDA work on gradients. So I think there's a very live and interesting ecosystem to understand the dynamics of the material we're working with. And so the last thing I'll talk about is a little bit briefly on coding and language models. There's lots of applications of language models people are building. I'm sure you've seen them: learning, teaching, writing assistants. My favorite one, doing administrative work that I don't want to. Coding tools is also a close favorite. It makes coding easier and more fun for me. Lots of stuff in marketing, and some stuff purely maybe for fun. Let's talk about coding a little bit. So this is an example. So you can see the full prompt text there. I want to make a game called Throwing Rocks at Orcs. The hero is a knight at the top of a tower. This is a game I played when I was a kid many years ago. And I was like, can you just make me a game like this in the web? And one prompt, you end up with a playable game, which is kind of ridiculous if you think about it. So vibe coding is definitely something that anyone can do, but it's hugely different what you can do depending how much you know. So unfortunately, that means there's a bunch of hard work that happens in understanding how is it that you actually use this stuff. And the other thing I'll say is that vibe coding and helping AI do coding is one of the most active areas of research. So in terms of what language models are going to be able to do in other areas, I think it's a very good area to watch. There's a huge landscape of different ways that people use language models to help with coding. You have the kind of closer to the existing human workflow, more code-oriented views, which is just an AI with autocomplete in your existing IDE, through to the end-to-end chatbot where you just say, make me something on the right-hand side. I think some of the important ones in between are command line interfaces, and then kind of dedicated studio applications. There's a bunch of zero code things that are there too. Right now, the ones I'm most excited about is actually the ones on the left-hand side, because they're building up basically the capabilities and seeing where is the limit and how much can we help. So those ones are ones that are, I think, undeniably useful. But on the right-hand side, on the very vibey end of things, you have the kind of aspirations of maybe we could just get what we want with software. Oh yeah, there's a really great talk by Andre Karpathy. If you haven't seen it, it's about how software is changing. It's well worth watching as well. This is an example of vibe coding. You put in a paper, you say, hey, can you make me the visualization in this paper? And by the way, make it interactive. This was a stunning success. Other papers I've tried have not succeeded as well. So this is definitely cherry-picked, but it's kind of amazing nonetheless. People making toys for their children. So I think the key thing about this is that it has changed the nature of coding. Coding is much less now about writing the code and much more about knowing what you want, getting the specification. There's an interesting anecdote that many people have noticed that MSc level teaching, the results from students has a higher variance. So this means that when you measure, you ask how good is the actual result that students have produced. Very often at the master's plus level, you get a bigger variance. So it's not clear that this thing is democratizing force on its own. And so in actual fact, it's like the more you know and the more invested you are, you can do far more. Whereas the bottom end of students very often just submit like, oh, here's my LLM done homework and nothing more. And it's not very exciting. This space is moving extremely fast. So this is, like I said, one of the most active areas of research, and it's what you can do significantly changes month to month. So conclusions and questions. I think LLMs are an amazingly versatile new material. They're incredibly easily to customize. Prototyping, language model configuration, and UX are keys for actually making responsible AI applications. The biases are configured. You have to choose and you have to measure at some level if you want to control for it and how you control for it. LLMs can explain themselves. There are lots of hot debates about how good this is as an explanatory device, but it is very often useful at some level. And the landscape here of prototyping with AI and developing with AI is rapidly evolving. And finally, the jagged frontier. It's amazing how smart they are, and it's amazing how dumb they are. And this actually is one of the most interesting things for me, like this really weird boundary between amazing capabilities and not great ones. And the knowledge you have can hugely change what you do with them. So with this, thank you for your attention, and I'll take more questions.
Thanks for the very insightful talk. I have a couple of questions. First of all, your talk was titled on the collaborative effort between humans and AI, and you do highlight the UX as a key element to it, but I'm wondering why you do not consider UI to be a key element. Like there has been a very upsurge of innovation in UI when software became predominant in human life. And I don't think the same UI interfaces are optimal for AI agents interacting with humans. And also, I'm wondering why do not touch upon multi-cooperative agents where agents are cooperating with other agents and how they interact, because it felt like the relationship is only unidirectional between humans and AI and not between AI and AI. So yeah, just want to get your opinion on those two facets.
Yeah, actually, there's the first one about what's the role of UI separate from UX. I wasn't actually distinguishing the two. There's lots of interesting things happening. AIs can generate UI much better than they ever could. You can draw a sketch and have the AI generate the front end code. Like UI itself becomes a medium. The main challenges here is that right now the tooling and infrastructure is not very good for telling you when and what is wrong with a UI. Getting language models to assess a UI is an area that needs significantly more work. But the UI landscape, in the UX landscape, in terms of defining what an effective application is and the responsibility aspects is absolutely key. The other question was about multi-agent systems. Yeah, the reason I didn't distinguish it is because from the perspective of a user, it's not multi-agent necessarily. It's one system you're interacting with. Like I think multi-agent is a view of how you architect things. The actual experience of developing multi-agent systems is a very young area. It's completely unclear whether the abstractions we have for agentic systems right now are going to be all thrown away in a few years. And I'll give you an intuition why that might be. In traditional front-end programming, for example, people used to do lots of message passing. Most agentic frameworks are basically prompt templates that pass messages back and forth. In front-end development, that is how we used to work. We used to work with lots of event passing stuff, but it was extremely hard to debug, to understand, and to build with. More recently, people have taken a more kind of data-centric view of that, and they said, actually, we want to have a notion of functional reactive programming where we have the notion of the dependency graph of how everything is actually related. How is the data related? And you make an explicit representation of how data is related, and that turned out to be a far better way to develop front-end programs. So if if the same abstraction ends up being better for multi-agent systems, it will look nothing like it does now in 5 years' time. But I think it's a very interesting question, and how you coordinate large amounts of inference is one of the key questions. And I gave a little bit of a discussion on the role of how is it you can spend inference for quality? And the fundamental challenge there is like, how do you know what quality is? That's your value function. If you have a good value function, you can spend inference and get quality. That means you can have a multi-agent system that does it as well.
All right, thank you so much.
Thanks. Here. Thank you for a very interesting talk. Very enriching. Get different perspective on many things that are very, very current. I wanted to see if you could expand a bit more on one of the aspects that you had in previous slide, which is this realization that LLMs as a tool have a very uneven effect in individuals. So we have at the same time papers bringing out, or studies bringing out the fact that they make quote unquote people dumber, in the sense that they basically don't make them exercise their intellect to solve problems. And at the same time, for certain people that have good criteria, good judgment on, they know how to extract the value and how to throw out the bad parts like hallucinations, they have this amazing multiplying effort, right? That can basically propel these things into being extremely impactful, right? And it feels like it's very asymmetric, and maybe even worrying, in the sense that it will create some boundaries between people and how they use LLMs. Do you have some more thoughts on that?
Here we go. This time I remembered to press the button. Like pressing the button, it's a very hard problem, actually, right? Like how it requires societal change, perhaps. But we're not the only place that has faced this. This is not the first time people have faced it. So in mathematics, a few months ago, I was at the Institute for Advanced Scientists speaking with mathematicians on the future of AI and mathematics. And one of the things that was highlighted there was that in mathematics, actually, they've wrestled with this problem. Mathematicians still learn how to multiply numbers. They still find it useful. They still find it useful to go through calculations that they know a computer can do better than them, because it develops intuition. It develops intuition in a very profound way, very differently than just getting a computer to do the calculation. So in mathematics, it's been the notion of like intellectual suffering at some level. This is actually what they called it, suffering. They said intellectual suffering is necessary. Now, in computer science, of course, we automate everything we can. And in some sense, we have a principle of laziness. Like, if I can automate it, I don't do it. And in some sense now, we might have to develop an appreciation for that form of intellectual suffering that is prevalent in mathematics. And we probably need to teach that too. It means it probably has to be in the examination frameworks, and it has to be like, oh, well, how is it you actually work with a language model to get something more profound? How do you do the critique about what you got? Like, at some level, I think it brings out the fundamental property of taste. How is it? In research, of course, we have this concept of research taste. What research is somehow tasty? It's this kind of ephemeral concept, but it's very profound. And in some sense, I think it will make an increasing demand on people understanding what they want, having taste, and being able to share it, which is, of course, also very prevalent in mathematics.
Here. Thanks for the great talk. So I have a question concerning the probe and the fact that I would like to understand why in the initial attempt to do that probe starts from someone thinking that there is something inside the model that we can interpret as the model thinking, quote unquote, that the user is a female or a male. Isn't that a lot of anthropomorphization?
It absolutely is. And so, there's different ways people try and get at this. So, you can try and make data sets where the model actually kind of answers it in a different context. You can try and do things like you saw with patch scopes, where you take the internal representation. So you first of all need to find like, okay, what is our ground truth? What's the notion which will say this is indeed a representation of the model? So in the case of this work here that I cited, what they did is they created the probes in many different contexts to try and make an assessment of like, does the model think that the person is male or female? And they validate it by actually asking the model in all these different contexts. So then the interesting thing is that in this context, in the context of a chat setting, the model will often say it doesn't know, even though the probe gives a very high score, and there's a correlational difference as well. So you're absolutely right to question this, right? Like what actually defines ground truth? You have to define ground truth. And so the way that it's done in many cases is you go, okay, what is the set of domains of discourse that we're concerned with? What is a data set that defines the correct answer? Then you train off your internals. You hope you pick the right layer or the right things. And incidentally, I didn't mention this actually, but probing has many different incantations. And like one of the ones that you've probably heard lots about is mechanistic interpretability and sparse autoencoders, because Anthropic is really good about talking about this. And Chris Ola is great on visualization. But SAEs are fundamentally a way to find probes in a unsupervised manner. Yeah, but the answer to your question is, yeah, you have to define your ground truth. And then every piece of scientific result you get and read depends on what you've defined as ground truth.
Yes, it's working. Hello, thank you very much for your presentation. So we talked about agentic system. For me, it's still a black box, and I don't understand the difference between agentic system and LLMs inside a loop with if else. So what is the difference? I mean, what is the definition for you? Is it just a fancy word, commercial one, or it's real thing?
I think there's there are textbooks on agentic systems that existed before LLMs. So they gave it a kind of particular characterization of like ability to act independently. So sometimes there are temporal distinctions you can make. Unfortunately, or I don't know if it's unfortunate or not, but anyway, the reality of the situation is that the terms are used rather indiscriminately. And so your definition of an if, with some loop around it, usually, if it's just a template with one loop, it's not usually called agentic. Usually, if there's more than one template that are somehow communicating, it's called agentic. And so, I mentioned this alpha evolve system, right? This is described in the press release as this kind of coding agent. But here there's I think there's 2 prompts, right? And then a loop strategy around it. It's basically what you said. It's a while loop with a prompt or 2 inside it. They do a couple of fancy things with substitute. They have a prompt sampler, so they substitute many different substitutions into the prompt to try and boost diversity. But it's really on the edge of probably what traditional agent systems research would describe as agentic. So personally, I use it. It depends who I'm talking to, but these days people use agentic in a very loose way.
Thank you.
Hi. Hello. Thank you for the talk. I think thinking about this interface of language is really important, but because we're using this highly evolved symbolic system to communicate. But what do you think, or what else could you do? Like, is language the frontier here of how to communicate with these systems, or is it a building block for way more interesting things? Because one of the consequences of having language as we have right now is that we are stuck with the computer in a sense, but we communicate with each other in a much broader way.
Yeah, I think it's quite early days. We're I don't know, you've probably seen some of the tech demos without public usage yet, but there was the Astra demo last year. Today you can take your phone and you can ask it to read your screen, and you can talk to it at the same time as it's looking as your phone screen. So the audio video capabilities are massively improving, and this means you can have far more embodied applications. So I think, the traditional notion of UI is very unclear what will happen. When software took a lot of work to develop, you would want to develop software that encompassed many applications because it was a big investment. But if the act of creating software is cheaper, maybe it makes more sense to create bespoke custom applications for every time you use the AI. So this is the kind of, we now have this, in a way, a fundamental question about how should the interaction look? And even what should the nature of interfaces look like? There are lots of challenges to creating dynamic interfaces. State management is still extremely difficult for LLMs, and all of the deployment stuff is extremely difficult as well. So, but it's a very, very busy space, and I expect the audio visual stuff to change. Already on your phone, you can say, point your phone and look at something. And even for the last few years, Google Translate had it, right? Like you can press the camera and you'll immediately get the translation in line. So I think we have lots of precursors to much richer interactions.
Here. Thank you for your beautiful presentation. I have two questions. The first one is, what's your take on small language models? And what's your opinion of how, what's the future of conversational agents that will exploit large or small language models in the future? Thank you.
I love small language models. They make science so much better, right? Like if I want to do experiments, it's really annoying if I have to scale up to a 100 billion parameter model or something like that. I actually think that from a scientific point of view, we probably haven't invested enough in bridging the gap between million parameter models and billion parameter models. I think there's 3 orders of magnitude there, and that we don't, like, we've got the scaling laws that are an attempt to guide us through this space. But actually, most of the time we assume that language is a very big artifact. So to capture the emergent phenomena of language, you need to train inherently a large language model to know if something really works or not. It's not clear to me that you can't take some of the fundamental ideas in language and scale it down and create toy synthetic languages that would be very indicative of what would happen at larger scales, but they will only capture a fragment of language. So there's a few papers in this space, like there's one called Toy Stories that was showing that you can create fluent output if you restrict the domain of discourse. And that's really interesting because that's kind of indicating that actually you probably can scale many aspects of large language models down smaller. However, in terms of chatbots, yeah, I expect fully that there will be enough capability in small language models that will live in your phone that you can have a discussion with. Chatbots, in terms of interfaces, you know, they're very boring in many ways. So I think it's much more interesting to ask the questions from an HCI or design or even, you know, future technology perspective of what's after chatbots. How is it that natural language integrates in many different ways? Or like the previous question, you know, the vision aspects. What are the different kinds of interactions that are going to happen as generative AI gets better? But language is, you know, people's incredible power of communication. So it will always be fundamental. But whether it's a chatbot per se or not, I think is a much more open question.
Yeah, sorry, you just gave me an insight into the fact that most of the time we are very surprised about how good are these models and generating text. And what we are not surprised about the fact that these computers are able to make calculations in, you know, just like that, millions, billions of numbers. We are not surprised. We are so accustomed to this fact. But I mean, basically what computers do is sums products and confrontations. So we basically exploit their ability to do so to generate text.
Maybe this should be the last question. I think people are getting a bit tired and we're running over. But I think, yeah, it's amazing. I think it'll be taken for granted. I have a 6-year-old daughter. She takes it for granted that she can talk to a device. That was not something I took for granted. And she even like gets frustrated when it doesn't know things. Like she asks it like, you know, do I have school tomorrow? And it doesn't know. All right, with that, thank you all again.
So just a few words about the dinner. So the dinner is at 8 o'clock, but we will have a welcome drink starting at 7:30. So whenever you want to go, you can have the drink. Most people will probably want to go by walking. It's like half an hour, right? Yeah, half an hour, 45 minutes maybe. And yeah, I'm sure that there will be groups going. If someone else wants to go by metro, you can get the green line and exit on Recio, okay? Okay, bye-bye. See you later.